Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we look at real matrices with complex eigenvalues. So because we're going to be doing work involving complex numbers, we're going to start by going through what they are and how to perform operations with them. So a number z is said to be complex if it's of the form a plus ib. So here a and b can be any real numbers, the numbers you're used to, and I is the square root of minus 1. So it turns out that the real numbers are a subset of C, the complex numbers. So any real number is a type of complex number, but not all complex numbers are real numbers. So these are very useful because they allow us to solve equations we previously couldn't. So let's say we have the quadratic x squared minus 8x plus 17 is equal to 0. Now if you go ahead and calculate the discriminant of this, you get discriminant equals b squared minus 4 times a times c. You get a negative number, negative 4. So you were probably told in some point in your life that means that there are no solutions to this quadratic. Well, it turns out that if we allow ourselves to square root minus 1, we can actually find two solutions to this quadratic. So using the quadratic formula, we have x equals minus b plus or minus the square root of the discriminant over 2. So, of course, the reason that you would have been told that there are no solutions is there are no real numbers that you can multiply by themselves to get minus 4. Square root of minus 4 doesn't exist in real numbers. But if we allow ourselves to square root minus 1, what we can do is this little trick. We can write the square root of minus 4 as the square root of 4 times the square root of minus 1. And, of course, square root of 4 is just 2. Square root of minus 1 is I. So, what we can now do, which we previously couldn't, is we can take the square root of a negative number, and of course that'll mean we can take the 4th root, 6th root, etc. of negative numbers, which we previously couldn't do. So I can come up with a solution. It's just 8 plus or minus 2i over 2, which gives us two solutions here. So the first solution is z equals 4 plus I. The second solution, similarly, is 4 minus I. So note that these two complex numbers look very similar. The only difference is the sign between the real and imaginary parts. So that's no coincidence. These two are called complex conjugates. So a complex conjugate of a complex number is the same number, you just change the sign in the middle. So if z here is a plus ib, complex conjugate written like that is just a minus ib. So complex conjugates are very important. The reason is if you add together a complex number and its conjugate, you get a real number. But you also, if you multiply a complex number by its complex conjugate, you get a real number. And that's why they come up as solutions to polynomial equations. It turns out for any polynomial that has real coefficients, like this one here, if z is a solution and z is a complex number, so too is the complex conjugate of z. So z, a complex number, and its conjugate always have the same length. We define the length, the size, if you like, of a complex number to be the square root of a squared plus b squared. Remember, z is in the form a plus ib. So for both of these complex conjugates there, their sign, their modulus, their length, whatever you want to call it, is just the square root of 4 squared, because a is 4, but b is 1, because 1i and minus 1i are the same. So it's the square root of 4 squared plus 1 squared, or the square root of 17. That's the measure of the size of z. So now let's look at performing the 4 operations with complex numbers. So let's say I have these two complex numbers, x equals 3 minus 4i and y equals 5i. So note that y has no real part. it is in the form a plus ib, where a equals 0. So let's say I wanted to add these two together. Well, that's really simple. All we do is add together the real parts, so 3 plus 0 is 3, and then we add the complex parts. Treat it like terms in algebra. So minus 4i plus 5i just gives you 1i. So x minus y, similar, 3 minus 0 is 3. We do the real parts, then we do the complex parts. Minus 4i minus 5i. So let's say I wanted to multiply these two now. I'm going to need to expand brackets. I have x, the whole thing, multiplied by y. So 3 times 5i, so similar to algebra, we just multiply the coefficients, so I get 15i. Now minus 4i times 5i, so I get minus 4 times 5, which is minus 20, I squared. But I squared is equal to negative 1, because I is the square root of negative 1. So this actually equals 15i minus 20 times minus 1. So that's my final answer. Let's say I wanted to do y divided by x. So then I have 5i divided by this. I want to write it as a fraction. Now it's kind of like when we had an irrational denominator. We rationalized the denominator by timesing by a conjugate. And we're going to do the same here. We're kind of going to realize the denominator. We're going to make it real by timesing top and bottom of the fraction by the complex conjugate of the denominator. So I'm going to times top and bottom by 3 plus 4i, because that's the same as timesing by 1. I won't change the value of the fraction, but I'll just make it easier to understand. So timesing the top, I need to expand brackets again, so I get 5i times 3. Now this time I'm doing 5i times plus 4i, so I'll actually get negative 20 over. So 3 minus 4i times 3 plus 4i is the difference of two squares. So you square the first, and then you square the second. And then, of course, you stick a negative between them. Now, 4i squared is negative 16. So what I have is, on the bottom, 9 minus 16. So I keep the same denominator, but then on the bottom I have 9 plus 16 giving me 25. That's all for the arithmetic of complex numbers. Now let's actually look at the matrices in which we're interested. Let's start by looking at this matrix A. Now remember, any matrix induces a linear transformation, as does this one here, A. So what kind of linear transformation is induced by A? It turns out that this matrix A rotates the whole plane 90 degrees anti-clockwise. What I mean by that is if you start with any vector and it's multiplied by this matrix A, it will rotate the vector 90 degrees anti-clockwise. So for example, if we had here the vector, which we can write as 2, 0, if I apply the matrix A to that, it will map it over here to the vector 0, 2. So you can see it's been rotated 90 degrees anti-clockwise. So let's look at this vector in yellow, which is the vector minus 2, 1. If I apply A to this, it actually gets mapped to the vector minus 1, minus 2. So that's this vector over here. So what's happening is this matrix takes any vector in the plane and rotates it 90 degrees anti-clockwise. So every vector will get rotated, except of course the 0 vector. So this might force us to think there must be no eigenvectors, because there are no non-zero vectors that are mapped to scalar multiples of themselves. There are no non-zero vectors that are only stretched, because every vector other than the 0 vector is rotated. But we also know that A, being a 2 by 2 matrix, will have a characteristic polynomial that's a quadratic. But I basically just told you that now that we have complex numbers, we can always find solutions to quadratics. In fact, there are always 2 roots of a quadratic counting for multiplicities. So the only way to reconcile both those things, the only way they can both be true, is if the eigenvectors are complex. That way we can find a vector that is mapped to a scalar multiple of itself. Of course, it's not actually a vector that exists. You can't actually draw this vector in the plane. So it's sort of rotated to a scalar multiple of itself. And of course, this could only happen if the vector in question were complex. So let's look at the characteristic polynomial of A. So it's the determinant of A minus lambda I. So it's going to be minus lambda times minus lambda minus the off diagonal elements multiplied together. Cleaning that up, we get lambda squared plus 1. So if I want to solve characteristic polynomial equaling 0, I have lambda squared plus 1 equals 0. Lambda's only in one spot, so I can just subtract 1 from both sides. Of course, I can't solve this without complex numbers. So lambda will be the square root of minus 1, which is I. It's also minus I. So they are the two eigenvalues. And note that they are complex conjugates, which is once again not a coincidence because of what I told you about polynomials before. So if you have a complex eigenvalue, its complex conjugate will also be an eigenvalue. So we know the two eigenvalues. Let's go ahead and find the two eigenvectors. So let's use lambda equals positive I. So then we get A minus lambda I. I just subtract I from the diagonal elements. Hopefully you can see why this matrix is singular. The second column is negative I multiplied by the first column. So of course I need to find a basis for its null space in order to find the eigenvector. So in this case, it's probably going to be easiest if I write out equations and then pick a value for x1 and find the corresponding value for x2. Make it easier on myself, I'm just going to pick x1 is equal to 1. Of course, there will be an eigenvector where x1 equals 1, so I'll just choose that. And solving for x2, I get x2 is equal to minus I. So, the eigenvector I have corresponding to this, so I'll call this lambda 1, then v1, the eigenvector corresponding to it, is 1 minus I. So it becomes important for calculations that we can decompose this vector v1 into its real and imaginary parts. So the real part of v is just 1, 0, and the imaginary part of v is 0 minus 1. So the real part of a vector just includes all the real parts of each of its entries, and the imaginary part of a vector is just the coefficient of I of each of its entries. And note the imaginary part of v is actually a real vector. So let's look at finding the second vector v2. It turns out we don't need to go through all this, thank God. So I know that if I have an eigenvector v and eigenvalue lambda, then this must be true. Now we're going to need to take the complex conjugate for me to show you how we can find v2 easily. So to take the complex conjugate of a matrix, all you do is take the complex conjugate of each of its entries. So for this matrix here, v1, the complex conjugate vector will be the same, but we take the complex conjugate of each of its entries. So it'll just be 1 positive I. So that's what I mean when I write this, when I take the complex conjugate of each side. Now, A is a real matrix. So that means it's equal to its complex conjugate. Same for real numbers. They're equal to their complex conjugate. So I can write it like this. A times the complex conjugate of V is equal to... Now, I can write this second one, because lambda is a scalar, I can write it like this. So what this shows is that if V is a complex eigenvector of a real matrix A, so too is the complex conjugate of V. And its eigenvalue is the complex conjugate of lambda. So, if V is a complex eigenvector of a real matrix A corresponding to lambda, then the complex conjugate of V is an eigenvector corresponding to the complex conjugate of lambda. So what does this actually mean? Well, I found that this was the first eigenvector, so that means that the second eigenvector is just going to be the complex conjugate of the first, which I told you before was 1 plus I. So that cuts down our work. Alright, sorry for the long video. Hope you've enjoyed it. This has been the luckiest maths teacher in the world. Have a great day.